Welcome to The Explainer. Today, we're diving into a strange little computer quirk that, believe it or not, reveals a deep truth about numbers, trust, and even reality itself. We're going to start with a puzzle you've probably seen: why computers sometimes seem to get simple math wrong. Then, we'll get under the hood and see how computers actually handle numbers. From there, we'll jump into the fascinating history of this system, how a technical standard basically became a global treaty on truth. And finally, we'll talk about why this error feels so weird to us and how you can turn it into a powerful teaching moment about critical thinking. This isn't about a bug, it's about a fundamental feature of our digital world.
All right, let's jump right in with Chapter 1, The Calculator's Little Lie. We're kicking things off with a mystery that you or your students have almost certainly bumped into. It's one of those moments that can be really confusing and honestly can make you question the tools you rely on every day. So you ask a computer a really simple question. You type it into a calculator, a coding environment, whatever. What is 0.1 plus 0.2? I mean, every piece of math intuition we have, everything we learned in grade school, screams that the answer is obviously, cleanly 0.3. But that's not always what the computer gives you back. Instead, you get something a little weird. Yeah, you see this 0.3, then a whole bunch of zeros and a tiny little 4 tacked on at the end. Now, your first reaction and your student's first reaction is probably that something's broken. Is it a bug? Is my calculator busted? But here's the most important thing to get across. This is not a mistake. In fact, the computer is working perfectly. It's doing exactly what it was designed to do. What you're seeing here is the computer basically whispering a secret about its own nature. It's showing you the gap between the perfect imaginary world of pure math and the messy, practical reality of building a thinking machine out of physical parts. This isn't an error we need to fix. It's an opportunity to talk about how things really work. So that brings us to Chapter 2, How Computers Count Fractions. To solve the mystery of that little 4 at the end, we've got to pop the hood. We need to understand a really key idea. Computers don't count using the same number system we do. We use base 10, the decimal system. They live in a base 2, a binary world. And that difference, well, it changes everything. The system computers use for any number that isn't a whole number is called floating point arithmetic. It's called that because the decimal point, well, the binary point, can float around to where it needs to be. Now, this isn't some chaotic free-for-all. It's all governed by a super important global standard called IEEE 754. Think of it as the rule book that makes sure every computer, everywhere, does its math the exact same way. It's the hidden engine of pretty much all modern computing. Okay, now this slide is a fantastic analogy for the classroom. Over on the left, you see our world, decimal base 10. We use 10 digits, and in our system, we all know that a simple fraction like 1/3 is impossible to write down perfectly, right? It's just 0.3333 forever. We just accept it and round it off. Well, look at the right side. That's the computer's world, binary, base 2. It only has 2 digits to work with, 0 and 1. And in its world, a number that seems super simple to us, like 1/10 or zero point 0.1, is an infinitely repeating fraction. It's that 0011 pattern, repeating over and over forever. So how in the world does a computer store a number that goes on forever? It breaks it into these 3 parts. First, there's the sign, super simple, just 1 bit to say if it's positive or negative. Second, the exponent. This part tells the computer where to float the binary point. And third, the fraction. This is where the actual digits of the number are stored. But here's the catch, and this is the whole shebang right here. The space for that fraction is finite. It has a limited number of slots. So to store that infinite binary version of 0.1, the computer has no choice. It has to round it. It stores the closest possible number it can. And when you add the rounded version of 0.1 to the rounded version of 0.2, those tiny invisible rounding differences add up, and you get an answer that's just a hair off from 0.3. And this leads us to our next chapter, a global treaty on numbers. The fact that your laptop and my phone both round numbers in this exact same predictable way, well, that was no accident. It's the result of a massive, decades-long effort to get all the machines in the world to agree on the truth. It's less of a technical manual and more of a diplomatic achievement, really. You can really see how this story unfolds over time. Back in 1985, the problem was simple. Computers from IBM and computers from, say, DEC would get slightly different answers to the same math problem. For scientists in the middle of the Cold War, that just wasn't going to fly. You needed results you could reproduce. Then in 1991, the stakes got tragically real. A Patriot missile system failed because of a tiny rounding error in its clock that got bigger and bigger over time. This proved that these microscopic errors could literally be a matter of life and death. Jump to 2008, and now it's the financial industry's turn. Banks can't have tiny rounding errors when they're dealing with trillions of dollars, so the standard was updated. And just a few years ago, in 2019, it was refined again for the world of AI, where being able to reproduce a result isn't just a technical need, it's an ethical one. This number you're looking at, it has a name. It's called machine epsilon. For most computers, this is it. This is the smallest possible gap between one number and the next one it can represent. It's the basic unit of rounding error. It's an error on this scale, building up over hours and hours, that caused the Patriot missile tragedy. It's like a little ghost in the machine, always reminding us that our tools are built on approximation, not perfection. So, okay, we've established that this error is real, it's there by design, and it is incredibly, incredibly small. But that brings us to Chapter 4, the psychology of almost. Why does seeing that little point 4 at the end just feel so wrong? The answer has way less to do with math and a lot more to do with our own minds. There's a perfect term for this feeling: cognitive dissonance. It's that mental static, that discomfort you feel when you're trying to hold two completely contradictory ideas in your head at the same time. In our case, belief number 1 is something we've been told our entire lives. Math is perfect. Math is absolute truth. And belief number 2 is what's staring back at us from the screen. Point 1 plus point 2 is not point 3. That clash right there is where the confusion and discomfort come from. And this really gets to the heart of it. The problem isn't sensory, it's symbolic. You could never ever physically measure the difference represented by that tiny 4. It's too small. But we don't see the tiny error, we see a broken rule. We see a violation of a mathematical truth that we hold sacred. And this is exactly why it's such an amazing teaching moment. It's a chance to talk about how we trust the systems around us, and how that trust is built on symbols and rules, not just what we can physically see. This table just lays it out so clearly. Look at the two scales. On top, you have machine precision. We're talking about 10 to the power of -16, just an absurdly small number. On the bottom, you have human perception, the smallest thing our eyes or ears can reliably notice. That's around 10 to the power of -3. The computer's rounding errors are more than 1 trillion times smaller than anything we could ever perceive. The machine isn't wrong in a way that physically matters, but it's imperfect in a way that symbolically matters a great deal. And this all leads us to our final, and I think most important chapter: truth, trust, and approximation. Okay, so now we know what's happening, how it works, and why it feels weird. What do we do about it? As educators, how do we flip this glitch from a moment of confusion into a powerful lesson? The most powerful shift we can make is right here. We have to reframe the word error. This isn't a flaw, it's not a bug. It is a necessary, natural feature of any system that has to describe an infinitely complex reality using finite tools. And that's not just computers. Think about a world map. It has to distort the globe to fit on a flat page. Think about language. We only have so many words to describe a universe of feelings. It even applies to our own brains, which use shortcuts and models to make sense of everything. So, here are 5 concrete things you can do in your classroom. First, teach tolerance over equality. Show students how to check if two numbers are close enough for all practical purposes instead of being perfectly identical. Second, use these errors as teachable moments. Stop the class and say, hey, look at this. Let's talk about how computers actually see the world. Third, broaden the conversation. Talk about how all representation has limits: maps, models, even art. Fourth, foster what's called epistemic humility. I love that phrase. It's just the wisdom of knowing the limits of what you know and the limits of your tools. And finally, explain that being open and honest about uncertainty actually builds more trust than pretending everything is perfect. Showing students why the computer does this builds a much deeper trust than just ignoring it. And so we're left with this big, provocative question to ask ourselves and our students. If perfect precision is impossible, even for our most logical machines, then what should we trust? Maybe the lesson here is that trust isn't about finding perfect, flawless answers. Maybe true trust comes from understanding the limits of our tools, from embracing approximation, and from learning how to reason with wisdom and humility in what is, after all, a beautifully imperfect world.